So, hi. Hey, everyone. Move away from. Welcome to the first talk this afternoon. This is Krzysztof, who works for Tweak, rose to fame when he was part of the team that implemented linear types in, GHC and Haskell. And like most programmers, he doesn't really like programming, so he writes programs that do the work for him, and he will talk about that today. Welcome.
Hi, everyone. This is a program in Python that prints hello world. This is a program in Haskell that prints a program in Python that prints hello world. This is a program in Haskell that prints its own source code. You can see that it prints. The string s, which is main equals put string line, and if you look at it closely, it will print exactly its own source code. This is called a quine. You can have something more complex, like a program in Haskell that prints a program in Python that prints back the original Haskell program. This is a GitHub project, there is a link there, that goes over 100 languages. So you can start at C, and this will be a C program that starts a prints a C++ program, that prints a C# program. You go over 100 languages, and you get back to where you are started. Or this doesn't even have to be a cycle. You can have a program in Haskell that prints a program in Python, then you have Haskell, then 2 layers of Python, then 3 layers, and so on. Or you can have a program in Haskell and a program in Python, and both of them print either the Haskell program or the Python program. And this one is technically more involved than the previous case, interestingly. So how do you do that? I will show you in this talk the principles that are behind those programs, so you won't think this is just some kind of trick that you can easily forget. First of all, quines are programs that prints the source code, so we need some way to manipulate source code in the program. And I will use strings in this talk. Now, whenever you introduce a type, you should think, how can you create values of that type, and how can you transform them? Like, what is the API of that type? Let's start with something simple. Let's try to create a value of type source code, a string. This is the carried addition function. This is a function that takes x and returns a function that takes y and returns x plus y. We can apply it to a single argument, and then we get a function that adds 42 to the input. We can delay this process to the next stage by using quotation marks. This is now a function that takes x and returns the source code of a function that adds x to the input. So we apply it to 42, and we get the same result as previously, except it is in quotation marks, and there is that double backslash because we have to escape When we have a normal function, we can apply it to a normal argument. If we have a delayed function, a function in quotation marks, then we can only apply it to a delayed argument. And that means really concatenating the two strings and forming function application that will happen at runtime. So this won't actually, if we do stage application of those two things, it won't actually do the function application. We'll only create a term that represents function application. And you can see that there is an operator precedence issue, so we also have to add parentheses. Now, the first function on the top of the screen here, this is the dollar in Haskell. This is normal function application. And for stage application, we will take the source code of f, the source code of x. We will put both f and x in parentheses. And this is how we get staged application. This will give us too many parentheses because they are not always necessary, but this is not a big problem. However, I don't want you to be thinking about those parentheses too much. So I will use pseudocode, and I will write it this way. I will pretend I can pattern match on code. So this means given source code of f and given source code of an argument, this returns the source code of f of x. And this is the actual implementation. This is just pseudocode. You can think of this as a template with placeholders. That is, we have some kind of, you can have a longer expression, and f and x are placeholders that have to be substituted with the values of the argument. Okay. We have normal application, we have staged application. However, we cannot mix those levels. Given a normal function, we cannot apply it to a delayed argument, and given a delayed function, we cannot apply it to a normal argument. And we cannot change the level at runtime. There is no function eval that would take a string and return the expression. So there is no function that would take the string 1 plus 2 and return the number 1 plus 2. Likewise, there is no function that would take the number 1 plus 2 and return the string 1 plus 2. So we have to, those two worlds are separate. Now, about quotation, let me make one thing clear. What you can do, if you are editing Haskell source code, you can put quotation marks wherever you want. But you cannot do that at runtime. If if at runtime you're passed a function, the only thing you can do with it is you can call it. You cannot inspect its source code. So quotation is there, but it is a special form. It is not a function. OK, so it looks like we have the unquoted world and the quoted world, and they are completely separate. There is no interaction between them. However, there is one thing that we can do, and it will be crucial for this talk, and I'd like you to look at this line. This is the Haskell show function used on a string. If we call show on a string, we will get the same string containing the original string as a string literal. So this, we give it a string containing 1 plus 2, and we get a string containing 1 plus 2 as a string literal. In pseudocode, you can think of it this way. We are given an expression e. We are given a string containing an expression e, and written a string containing the expression e. Of course, this is not how show is actually implemented. It has to add quotation marks at the boundaries of the string and escape any backslashes and quotation marks inside of the string. OK, so to recap, this will be our toolbox used for the rest of the talk. We can use string literals to write source code. We can combine them with templates, as in the staged application example earlier. However, when we do that, the quotation level has to match. But we have the show function to add more quotation levels. OK, it's time to write a Quine. A Quine in pseudocode will be a function that will be some kind of identifier that prints its own source code. So this is how we would write it in pseudocode. But the problem is this is recursive. And when I showed you the toolbox, we didn't have recursion there. And Haskell doesn't have a stage recursion construct. So what can we do? We modified addition to get staged addition. We modified application to get staged application. Can we modify recursion to get staged recursion? Well, the problem is that in Haskell, recursion is built into the compiler. A definition is recursive when it refers to the earlier name. So we could modify GHC to support stage recursion in some way, but then we wouldn't be writing a Quine in Haskell. We would be writing a Quine in some kind of different language. So we have to do something else. We have to bypass this and somehow write a recursive definition without relying on built-in recursion. And there is the Y Combinator. This is a tool in the Lambda calculus that lets you express recursion without when the language does not have it. Now, this part of the talk is more involved. I ask you to follow, but if you won't follow all the details here, don't worry. I'm sure the examples will make it clear. So the normal fixed point combinator is a self-application. We have this function, and it is applied to the same source code. We can now this is a function. This is the body of it is f applied to xx, and we need to apply it to lambda x f of xx, which means we need to replace every occurrence of x with this lambda. So we get f, and then we need to say xx, where x is this thing. So we print it twice. And finally, you can notice that the entire argument to f is exactly this the initial fix we started with. So this is equal to f of fix f. Notice that we have this symmetry. We have x applied to x here, and the entire term is applied to itself. Now, can we modify the fixed point combinator to give us stage recursion? That is, to give us a string containing fix f. Well, it seems that we would have to put quotation marks somewhere, but where do we put it? There are so many places. It turns out that once you start doing the process, everything is forced, and there is only one way to do it. First of all, it's pretty clear that we need to put quotation marks here, because in the final results we want the quotation marks there. But now, notice that this is staged application. This is the string x applied to itself, which means the parameter to the function has to be a string as well. But if the parameter is a string, then this means the argument has to be a string as well. But now we have asymmetry. Previously, the function was applied to itself. Now the function is applied to its source code, which means we have the level mismatch problem. We are using unquoted thing when we should be using an unquoted one. And this means we have to reflect the same asymmetry in the self-reproduction recipe inside of the Y Combinator, which means we need to put quotation marks there. And finally, because we are using this write term twice to write to here, we need to put the same quotation marks there. Oof, this was a lot of work, and don't worry if you didn't follow it. The point that it can be done. There is, however, one more problem. if you look at this is our final result. However, there's one problem. You can see that this f here it is used normally, and here this f is under quotation marks, and this is also a level mismatch. We cannot have an unquoted argument and use it under quotation marks. And the solution is that we will pass both the function and its source code to sfix. Okay, it's time for a demo. I have GHCI, and I modified it so that it will not output the prompt. I can type 2 + 3, and I get 5. I did that because when we have a Quine, we want to see that the input and output match exactly. So when we have the prompt, it will be aligned. Let's try sfix. So we need to give it a function. We'll use pushString line, and we now have to give the source code of that function. And we got this thing. What is its type? This is IO unit. And if I run it, I get exactly the same thing we started with. So a Quine is a staged fixed point of the print function. But the nice thing is we didn't just get a Quine, a program that prints its own source code. We got the entire stage fix combinator, which means we can do a lot of many more things with it. How about a program that prints its its source code twice? Well, I can just do pushString line twice, and now I have to write the same thing in quotation marks. And because Haskell uses backslashes both for lambdas and for string escaping, I have to escape that. And we get an expression which prints its own source code twice. But those backslashes are annoying, and I will use a feature of Haskell called quasi-quoting to remove it. I will write this h, and this h simply means whatever is in those brackets should be treated literally, and we do not have to escape backslashes or quotation marks inside of it. This is only for our convenience of presentation. The programs that will be generated in this talk will never use h. This is only used for convenience when we input them. Okay, how about a program that prints its own length? Well, we have to change pushString line to print. And now we got a program that prints its own length. Well, that's not what we want. We are running the program, but we want to see the source code of it. So what can we do? Well, we add one more layer of quotation marks. This is our sfix function, and it is running the function f. We want to see the source code of that first, so we put quotation marks at the top level of the right-hand side. We put the outermost layer of quotation marks belongs to sfix2. This is the name of the new function. And there is one more thing we gain from that. Notice that previously we had to pass both the function and its source code at once. But now the entire right-hand side is under a quotation mark, which means we are no longer running the function f. We only need its source code, but we don't need the function itself, which means we don't have to pass it. We now get a function from string to string. And let's play with it. How about the example from earlier? I will call this A. So A is a string. Let's print it out. This is a program. Let's run that program. This prints 144, just like previously. And the length of that string is 144. So this is a program which has 144 characters, and it prints the number of 144. And notice we got it in by general means. Like we could use the SHA hashing function, and then we would get a program that would be printing its own hash. And you don't need to break cryptography in any way to get that. Also notice that this 144 is the same as this 144, which means we can define sfix alternatively as f of sfix2 quoted f. So only this is a function from string to string, and we need to apply the function only to the outermost layer to get the same effect as sfix. Okay. But you might object. You might say, this is not a Quine. A Quine is supposed to be a Haskell program. And what I've been showing so far are Haskell expressions. Well, let's try to fix that. This is a program that prints, that prints its own source code, the first one we've written, and we could add main equals to the front. But this is no longer a Quine because when I run it, it won't print this main equals. So how do we fix that? Well, we can just tell the fixed point combinator to print an expression which prints its own source code prefixed with main equals. So this is now a program which prints main equals, and then it prints its own source code. So I can run it, and now we get a normal Quine. But there is nothing special here about main equals. We could add here a type signature or the module header or helper functions. For example, notice that we've been using this show function. And in Haskell, we have it in Prelude. But if you'd like to write a Quine in a different language, you might have to define main inside of the Quine. So then you could write it here. You could define show here. And speaking of show, let's try this. What is this? Remember, our original Quine was this thing. And now we added this call to show. We added yet another layer of quotation. This is a program which prints its own source code, but not normally. It prints a string literal containing its source code. So I can run it. And now you see that it didn't print main equals. It prints a string containing main equals. Well, this is a bit weird, but it so happens that this is not just a Haskell string literal. This is also the way you write a string literal in Python, which means I can wrap it in a call to print. And now I got a program in Haskell. I will say main equals. I will run it. I got a program in Python. Let's jump to Python. Oops. And we got a program in Python that prints main equals, which is exactly the same as this. So this is now a program in Haskell that prints a program in Python that prints back the original Haskell program. And we can go further. Let's clean this up. Let's use point-free style. You can see that this is really a pipeline with 3 different steps. We have putting a string. We have a transformation, which takes a string and returns a program in Python that prints that string. And we have a conversion from a Haskell expression to a Haskell program. So we have first punt string line. Then we have a function which takes a string and returns a program in Python that prints that string. And finally, we have a conversion from a Haskell expression to a Haskell program. And this works as well. But you can see this structure of the transformations better. You could add here, for example, the reverse function, and then you would get a program which prints its own source code reversed. Or you could add a compression function, and then you would get a program which prints a zip file containing its own source code. Or you can add a compile function, and then you would get a program which prints its own machine code. But we can just add here, let's just add here another stage. Let's add Ruby. In Ruby, use put to print a string. So I will just add Ruby as another step. Let's try it out. We got, and again, I will say main equals, and copy paste that. Let's run it. We got a Ruby program. So now I have to jump to Ruby, and to do that, I will run Nix shell and jump to Ruby. I will copy paste the string to Ruby. And I got a Python program. So let's jump to Python. And this thing is exactly the same as this thing. You believe me? Okay. Okay. This is exactly the same. Oh. I think the terminal is doing something funny, but it's exactly the same as this. Okay. And if you remember that 128 programming language Quine I've shown you at the beginning, well, now it doesn't look so hard, except it's not as hard, and not as easy as you might think, because in most programming languages, you use the double quotation marks to print a string. And you can already see the problem here. What happens is that every time we call show on a string, the string has to be escaped, and the number of backslashes is doubled, which means if we use it for 100 languages, it will be simply too large. And the solution is that we have to offload some of that escaping to further stages. So instead of constructing the whole, instead of having both Python and Ruby just print a string literal, some of those stages will have to perform escaping, so that at no single moment we have a huge explosion. And despite all the fancy higher order stuff that's going on, remember this is just a simple function that takes a string and returns a string. Like this is, I am not cheating you in any way. This is just a string, and sfix is combining the string to get a Quine. So you could create a program where you have a lookup table where we map Ruby to this string, we map Python to this string, and then you get a configurable Quine where you enter a sequence of programming languages and you get whatever Quine you would like. The only thing you need is a driver language. In our case, it's Haskell, and a function written in Haskell for every programming language you would like that given a string will create a program in a given language that prints that string. So you don't even need to know, Ruby. The only thing you need to know about Ruby is how to print a string, nothing more. Okay. Now, if you look at the type of sfix and the sfix2, as a reminder, this is taking a function, the source code of that function, and returns the self-referential program. And this is just taking the source code of the function and returns the source code of the self-referential program. But this type is polymorphic. So far, we used it with IO unit actions, but we can put any type we want. So what type should we pick? Well, let's try a function. This looks pretty complicated, so let's do the normal non-stage fix combinator first. Let's just write the factorial. F of f minus 1, 5. So the way this works is that we have a function that takes as n, and if it's 0, then it returns 1. Otherwise, it calls the function f. And the magic of the fixed point combinator is that this function f will be exactly the same function that we define. If we use this with the, fix lets us refer to the function that we are defining. If we use it with staged fix, we won't get the function we are defining. We will be getting the source code of the function that we are defining. Let's try this. Our function will print the number, and then we could print, well, I will call it qf. Q means quoted version of f. And I could print the function, but if we are printing a stage function, if we are printing a delete function, the logical thing to do is to apply it to something. So let's apply it to n+1. So we use staged application, and we construct an application of the function f to, let's say, n+1. So let's try running that. Well, it's a function, so we cannot run it directly. We have to pass an argument. So let's pass 1. This is a program that prints 1, and a source code of a program that prints 2, and a source code of a program that prints 3, and a source code of a program that prints 4, and so on. So this is a bit like a Quine, except it remembers its generation number. Every time you run it, it increases that internal counter. Let's trace it again. Here we are printing that internal counter, which is the parameter to the function, and then we print the source code of that function applied to n+1. And this is why the number increases every time. And of course, you don't have to just have an increasing sequence of numbers. You can have arbitrary transformation, and the Quine effectively contains some kind of a payload that you can change at every iteration. But do you remember that previously we had a program in Haskell that printed a program in Ruby that printed a program in Python? Like we wrapped a Quine in a layer of Python and Ruby. We can do that as well here, but we can have different wrapping depending on the generation number. Here's what I mean by that. I will put additional parentheses here. And this is our normal. This is just a coin that remembers its generation number and is applied to increasing numbers. I will iterate a function that takes a string and returns a Python program printing that string. And I will iterate that function n times. Let's try this. Again, this is a function. So we have to apply it to something. Let's apply it to 2. You can see that we got a program that prints 2 layers of Python. So let's run it. Sorry, what have I done? Yes, let me just go back. We applied it to 2. We got this program. Let's jump to Python. Now so that Python program prints a Python program. Let's run it again. And now we got a Haskell program. But notice that while previously the source code ended in the number 2, now we have the number 3 here. Which means I can go back to Haskell. And now when I run that program, it will print 3 layers of Python instead of 2. And you can see that 4. So this is now a program in Haskell that prints a program in Python, that prints another program in Python. And then we have Haskell, and then we have 3 layers of Python. And then we have Haskell, and then 4 layers of Python, and so on. Like, if you remember at the beginning of the talk, I have shown that. Since SFIG is polymorphic, we can use another type. And let's try. Well, what is the simplest thing we can do? Well, let's try a string. This A will be a string. What will happen then? So we need to pass the identity function. And we got this thing. Maybe I will call this A. So we have a string A. If I print it out, I get this. This is an expression. What is its type? This is a string. So this is an expression containing a string. Let's evaluate it. We get this. So this is and A is this. So this is an expression which contains a string, and this is an expression which evaluates to a string, and the string it evaluates to is equal to the source code of that expression. Notice that this is not true for a normal string. Like if I have true, this will just evaluate to true, the Boolean true, but that's not the same thing as we started with. That's not the string true. And notice that while sfix id works, if we try the same thing with fix id, this will be an infinite loop because, this is as if you wrote as let x equals x in x. Okay. Now I'd like to go to another topic, which is multi-quines. So far, in this entire talk, every program in Python and in Haskell was print that string literal. And this is a bit unfair because all the work was done by Haskell. Can we do something else? Well, let's go back to the program where we had a Haskell program printing a Ruby program, printing a Python program, and I can write it as a system of equations. We have a programs P1, P2, and P3, one in Haskell, one in Ruby, one in Python, and P1 is prints P2, where P2 prints P3, and P3 prints P1. Now, the way we solved that system of equations is via substitution. We took P3, and we said, since P3 occurs just once, let's substitute it here, and then P2, since it occurs only here, we will substitute it here. And now we have just a single equation. We have a program in Haskell that means a program in Ruby that means program in Python that means P1, where P1 is the original, where P1 is the source code of the Haskell program. So we can use sfix2 to solve it. Now, is there a solution that is more fair, that is more symmetrical? There is one, but the problem is if I was to explain it here, there's a very big temptation to just substitute things. So I will show you a program where this is not possible. This is called a multi-quine. Let's try writing a program P1 and P2, one in Haskell, one in Python, and they will both have the same output. They will print both P1 and P2. Now the situation is different. Notice that so far in this talk, every program in Python was print exactly that string literal. But if we have only that power, then we cannot do P2, because P2 is a program that prints P2. So this is not possible if the entire program is print as string literal. We need something more. We need the sfix machinery in Python as well. And there are two ways to solve this problem. I will call them nested and flat. Since in Haskell nested is better than flat, let's do the nested solution first. Let's focus just on the second solution, on the second equation. You can see that P2 is a program that prints P2, but we don't know what P1 is. P1 is that equation, but let's forget about that equation for a moment. If we don't know what P1 is, the logical thing to do is to make it a parameter. We have a function that takes P1 and solves this equation. If P1 is fixed, then we can solve it using the sfix2 operation in Python. And notice that since sfix2 is just something that takes source code and returns source code, we can implement it in Haskell. That means we will use Haskell to generate Python source code. And you can see that we simply take P2, and this is basically the same idea, except it is a parameterized Quine. This is a program that prints P1 and its own source code. But if we have this f of P1, if we know that P2 is f of P1, then we can substitute it here. And now this equation in P1 does not refer to P2 at all, which means we can use normal sfix to solve it. And in a sense, we are combining here two fixed point operations. We have a fixed point operation for Haskell, we have a fixed point operation for Python, and we got a fixed point operation for the pair Haskell-Python. And mathematicians have figured out that there is a way to combine fixed point operators, and there is a monad for that. I'm not kidding. It is called selection monad, and that way is called Beckich lemma. Now, Beckich lemma is for normal Y Combinator, and what we are doing is a staged equivalent of that. The flat way is maybe a bit more straightforward. Instead of using the normal Y Combinator, we modify it to take a pair. So if you think of f1 as a function that, as a Haskell function that takes AB and prints one A applied to the pair AB and B applied to the pair AB, and you do an equivalent function in Python, and you try to evaluate f1, f applied to the source code of f1, f2, f, and the source code of f2, then you will get the solution to the original program of programs P1 and P2 that both print P1 and P2. Notice that to write this program, we need that in Haskell we are able to form function application in Python, and in Python we need to form function application in Haskell. So we need a heterogeneous version of the staged application primitive I talked about earlier. Okay. That is enough demo for now. I'd like now to give a few technical comments. First of all, in the normal Y Combinator, if you try to write it in Haskell, you will get an error. It will tell you that there is a mismatch and you would need a type T0, which is equal to T0 applied to T. But this is some kind of infinite type. You cannot have a T0 which is equal to T0. You cannot have a type T0 which is equal to T0 function T. Right? This would be some kind of function that goes all the way. So why we are not able to write the Y Combinator in Haskell, but the stage for this combinator works? The Y Combinator is a tool in the untyped lambda calculus. If you forget about the types and you just follow the symbolic transformations, the transformations symbolically, then everything just works. The problem is assigning types. And for the untyped version, there is no problem. For the typed version, the issue is that the typed lambda calculus is a vehicle for theorem proving. In other words, when we write the lambda calculus term, its type can be used as a tautology. And in case of the fixed point, if you type fixed ID, well, this has type A. This has any type T, which means once you have the fixed point operation, the system as a logic is inconsistent. There is no such problem with sfix ID because then we just get a string. And you can even write sfix in Agda, which is a language which enforces totality. Now, why does the same argument does not work? Well, the stage Y Combinator erases the type distinction. We wrote in a typed language in Haskell, but what we did is we assigned every program the type string. And things will be different. So 1 plus 2 will have the type string. But if we assign the type code of int to the string 1 plus 2, so if we index every string with its type, like template Haskell does, then you cannot write the normal the stage Y combinator, out of the same reasons as the normal Y combinator. Now, I'd like to study this formalism more deeply. Previously, at the beginning of the talk, I've shown you the toolbox. We had stage application, we had the show function, and those functions just operated on strings. But if we are indexing the expressions by their type, then we can have a more refined version. The stage application takes code of a function from A to B and gets a code of an argument and returns the code of the result. Likewise, the show function takes a code of something of type A and returns the code of A. And this type kind of shows why the show function is so important. You see, when you write a Quine, in a sense, you are removing executing a program is removing one layer of quotation. And a Quine has to output itself. So if executing a program removes one layer of quotation, we need something that gives it back. And show is the function that adds more layers of quotation. And the other two forms we have is that given an expression, we can form strings, and we can form a string as long as there are no free variables in it. And we have staged application. Now, mathematicians have studied that formalism before. Just like lambda calculus is the Haskell abstraction of writing functions and applying to them, the modal logic is the mathematical abstraction that is behind staging. So what you can do is you can think of those three things as an abstract term without any connection to programming. You just think this is one formula, this is another one, and there are many things that can be said about it. And in this formalism, you cannot define the stage fix operation because of the reasons I've mentioned earlier. However, unlike the previous situation, it is possible to add it as an axiom. So if you take Agda, a language which is consistent, and you add the fixed point combinator, well, you won't be allowed to without the discipline termination checker. But sfix2 can be added without violating consistency. This is called modal logic GL, and this is the logic that is behind Gödel's theorem. Okay. Now, so far we used sfix on the structure of Haskell expressions, and for a brief moment we had also Python, and we also had the pair Haskell Python. But it is possible to use sfix on a different structure, and to understand that, I'd like first to show you this is sfix and sfix2 used in the talk. It looks horrible, but we can clean it up. We can write it this way. This percent is the staged application function. So it takes the source code of a function, the source code of an argument. And sfix, you can see that there is the Y combinator here. So it's lambda x, f of x applied to x, lambda x, f applied to xx. You have to squint to not see the staged application and show, but if you do that, you will see this is the Y combinator. But if this is simpler, why did I do that for presentation? Well, the problem is that you have this percent, the staged application under the quotation marks. If you do that, this will work, but the resulting Quine programs will rely on the fact that percent is available in Prelude or something. So in order to make the presentation self-contained, I use that more complex version. And this is why there are so many parentheses here, because I have inlined the percent function. And we did that in Python. We did that in Haskell. Doing that in Python is very much the same, because instead of a lambda, we use the Python syntax for lambdas. But what if a programming language does not have lambdas? What if you would like to write a Quine in a programming language which doesn't have a lambda? Well, it so happens that you can do that. And the trick is that so far our programs were valid code that represented a function. But instead, we can have a string which is a template, which is not valid code, but it has a placeholder that can be substituted with. So instead of staged application, we'll have string substitution. We will have A will be this template, and we will replace every question mark in this template with B. So this is how you can simulate function application if the language does not have functions. If the language does not have functions, if you cannot program in a language with functions, well, you can have at least metaprogramming with functions. And this sfix2, maybe I should have written them side by side. This and this is exactly the same, except that I remove the lambdas, and instead of x's, I have those question marks. So those are the placeholders, and we will replace the function argument with the, we'll replace those placeholders when we are doing staged application. But the question is, what kind of programming language does not have lambdas? No. I am looking for a language that every one of you uses. No. The Haskell type system. We can define, the Haskell type system has strings, they are called symbols, and we can define the staged application and the show function, and we just repeat the definition. Time for a demo. Let's define a proxy type, and proxy, and now I have to add the quote. This is now a template, this is just like lambda x proxy x. And you can see we got this. Let's use string line. So we got this type. And if I evaluate that type, I get proxy applied to the source code of that type. Okay, so this is a type level stage views comparison. You can see that this is the source code of that expression, is exactly the same as this. So this is a type which is equal to proxy of a string containing the source code of that type. Okay, it's time for the last challenge. And this one is more difficult, and unfortunately I don't have a demo for that. You will have to believe me or type check things in your head. Here is we have a program which enumerates all proofs in arithmetic until it finds a proof that that program terminates. If it does, it terminates. And does it terminate? Well, that looks like an interesting puzzle. And how would we solve it? First of all, we are talking here about proofs. So we need some kind of proof checker. And we cannot like reuse a Haskell type checker on an Agda type checker because a type checker runs at compile time, and we want to run proof checking at runtime. So we will assume that there is some kind of function that takes a string, which would be a supposed proof, a string which will be what we want to prove, and a Boolean. So if you give it a valid proof, it will return true. So how do we write now this program P? Well, we can use sfix. This is now lambda P. So we are writing now a program whose source code is P, and it goes through every possible string. We can enumerate like first all strings of length 1, then all strings of length 2, then all strings of length 3. And we call the function proof if that proof function says that S is a valid proof of the fact that this program halts, then we exit. And notice that a priori, this program might halt or might not halt. It is possible that there is a proof, and in that case, the program will halt and the proof is correct. Or maybe there is no proof, and then the program runs forever, and there is no contradiction. So which is it? Well, it will definitely depend on the function proof. If we have, if our proof system is faulty, maybe it says true, this is a call root for anything. Maybe that function always returns true, and this program will then halt. Maybe that proof function is always saying false. This is never a valid proof. In that case, this program will run forever. But what if we have a sensible proof system? Well, what we want to know is whether this program halts. This is a property. But notice that the input to the proof function is not a property, it is a string. And you might see some resemblance to what has been done earlier in this talk. So we have a property and we have a string. However, what we are really interested in is whether the proof checker will say that this program halts. So this prov means there is a proof I of the property that this proof S returns true for something. And in general, you might imagine that this program halts, but the proof system might be not smart enough to see it. So in this case, the property will be true, but this will be false. Or maybe this program doesn't halt, but our proof system is inconsistent and it will say it halts. So those two things are different. And a priori, one might be true, another false. But in case of our program is looking for a proof that this program halts and terminates if it finds it. Well, in that case, if it finds a proof, then it will terminate. So we have a program such that if we can prove that P halts, if there is any such proof, then the program will halt. let's abbreviate that to a triangle. This is the same thing, I am making an abbreviation. So this triangle both encompasses probability and a quotation mark. Well, if the proof system is decent enough, it will also see that this implication can be proven inside of the proof system. But this type is the perfect argument for a triangle version of SFIX. As long as the proof system has the properties I talked about earlier, you can have a triangle version of SFIX, and this means we are using SFIX not to build a program, but we are building a proof, and we are learning something about how this proof operates. But I've told you earlier that you cannot use SFIX when the code is indexed by proofs, and that's what we are doing. Well, the solution to that problem is that we use SFIX on the type level, as I've shown you earlier with proxy. And the exact details here, you can look up the loops theorem, and there are references in the talk. This program will terminate, but it takes 3 layers of SFIX here. One is we need to define the program. We need to write the proof that this program terminates. But because this proof uses the fixed point combinator, it won't normally type check unless we use SFIX on the type level to make sure it does. And this was our program. If you add this note, if we are looking for a proof that this program does not halt, and if we find such a proof, then this program will stop. What will happen now? Well, if it finds such a proof, then it will exit, which means the proof that it found is false. And it really means that the proof system is inconsistent. But if this program doesn't halt, then there will be no proof of this fact because it goes through every possible proof, which means either arithmetic is inconsistent or the fact that this program halts cannot be proven inside of arithmetic. And this is Gödel's second incompleteness theorem. Okay, I'd like to finish this talk with a quote I found pretty cool. Given the nature of the multiverse, everything that can possibly happen will happen. This includes work of fiction. Anything that can be imagined and written about will be imagined and written about. If every story is being written, then someone, somewhere in the multiverse, is writing your story. To them, you are a fictional character. What that means is that the barrier that separates the dimensions from each other is in fact the fourth wall. And I think it's really nice to think of the fourth wall as the quotation mark. And I guess if you start thinking about the person, you are engaging in some kind of real-world grind. Okay, here are some references if you are interested. And that concludes the talk.
Thank you so much. I'm very pleasantly confused. Any questions from the audience?
This side?
Yes.
Hi, thank you for your talk. I have a question to the project you showed earlier at the beginning of the cycle, doing one Quine after the other after the other. Is there any language that doesn't go well with the next one? So do you know?
This is not my project.
I know that.
But there is a blog post where the author describes that the biggest difficulties were somewhere along here, where there was Perl and Piet. Piet is a language where the input is an image, so they had to write they had to write a program that creates that image, and I think they were saved by the fact that Perl has everything and something like that.
Okay.
But you can look for that, and there is a more detailed description.
Thank you.
My first question is, do you have the slides published somewhere?
I will publish the slides. I will also, in the interest of transparency, this is this is the entire source code that used for the talk. So you have SFIX, SFIX2, the SFIX2 for Python, and this is the stage application on the type level. I will I guess we can link the slides from the YouTube video once it's published.
I was just about to say, speaking of self-reference, this is me announcing that this very video will be uploaded later today.
You had a second question?
Yes, or maybe more assertion. The SFIX, the staged fix, I'm quite reminded of the Y combinator in Haskell because because you can write the Y combinator in Haskell if you just use a new type
Yes, yes.
to declare an equation.
I thought whether to include that fact in the talk, but
okay.
you know,
Yeah.
you have to cut something. Yes. So maybe I will show it now. If you use YF, you would need a type T0 that is equal to T0 ROT, and you can define a new type, and that new type won't make those two things the same, but you can use the new type constructor and deconstructor to convert between them. And this way you can build the stage fix combinator in Haskell, and this is also the reason why you cannot define that new type in Agda, because Agda is supposed to be consistent. And at the end of the talk, I've mentioned lib theorem, and then what you can do is you can create a type T0, and there is an additional code constructor there. So you have a type which is equal to code of the type to T, and then you can use the staged Y combinator on the type level to solve that problem.
Thanks.
Thanks for the talk. I'm a bit confused on what is the takeaway for your last slide. Is it related to the Gödel incompleteness theorem?
Yes, this one.
Yeah, I think the final slide. Yeah.
So if arithmetic is if there is like what you can show is that this program halts exactly if there isn't a proof that this program halts, and if arithmetic is consistent, if you add additional assumption that arithmetic is consistent, then you can prove that this program won't halt because halting will demonstrate the inconsistency of arithmetic. So maybe I wasn't completely clear, but this is the essence of the Gödel's second incompleteness theorem. For the first one, you just need the stage fix on the type level, which was earlier.
Okay, thank you.
And I should say that the real difficulty in like the general outline is improving Lick's theorem is that, but the difficulty and what is usually skipped and considered obvious is proving those three terms. So to show that you have a proof system that proves that if there is a proof, then if there is a proof that there is a proof, it takes some work.
If we have no more questions, then we also have no more time. So thanks again. That was really cool.